Hello, it's me, and I'm going to show you and demonstrate some slightly newer puzzles that I have, which is really derivations from older puzzles. These are crazy 3x3 plus 4 circle face and 2 circle face. Now, just to give you a little bit of perspective here, it really all starts out with a puzzle much like this over here. This is actually a circle cube. It says Mercury, but just ignore that. I really probably should peel that sticker off. But this is a circle cube where every face here is bandaged. Every center here is bandaged. I went through a little tutorial on how to do this with my reboot of the Earth circle cube, or crazy 3x3 plus cube. But the thing to demonstrate with this is the fact that even though these have circles that are stationary, these stationary circles really don't provide much in the way of complications with the scramble. This is actually a full circle cube that I modded a long time ago, in that the association of these inner circle edges here don't really change in terms of how they're oriented with each other. So this never makes it down here, never makes it down here. It always stays stationary. So no matter how I scramble it, the only thing I'm really scrambling is I'm scrambling the outer edges and the outer corners, and just sort of shuffling around these inner circle corners as well, but they still maintain an association with other aspects of the puzzle. For instance, this edge always has the same association with this inner circle corner. So this outer edge maintains an association with this inner corner over here. That if you notice, no matter what I do, no matter how I turn it, this edge is never separated from this inner corner. So because of that, just by shuttling this around, I'm shuttling this around. And because these guys never leave their specific orbit, I can just sort of put them in. So really the solve of this is much like the solve of any supercube, and I demonstrated that before. If you want another reboot of that, I can of course do that. But in any case, that's really where that is. Now, to enhance the challenge, they came up with a crazy 3x3 plus series. And with the crazy 3x3 plus series, as demonstrated, say, by this Saturn cube, is they would have certain ones that were fixed, certain ones that were bandaged. So this center is fixed over here, this center is fixed over here, but then they had centers that weren't fixed, that actually moved just like a 3x3. In a circle cube, these edges would never leave their orbit. It would always stay here. It has no place to go aside from here. With a crazy 3x3 plus series, I can take this edge, move it to one of these fixed centers, and I take it out of its orbit, which means it enhances the scramble, because when I scramble this up completely, suddenly this is now where it needs to be. I had to do some fancy handwork in order to put that back where it has to be. What's more, the association of this outer edge with these inner corners were also broken, because when I turn this, unlike here, if I turn this, I'll never separate this corner out from this edge. Here, I will separate this corner out from this edge, and that enhances the solve as well. So I went through these one by one. Now I have these guys. These are also called crazy 3x3 plus puzzles. But what they have is they have only certain centers or certain sides that have circles. The rest don't have circles at all. Now this is actually an older puzzle that I have. This is a Whit-Eaton product, but it's really exactly the same thing as what's called the crazy 3x3 plus 2 circle face, in which you only have 2 circles, 2 faces that are circles and the rest are not. This is the 4 circle face, where obviously you have 1, 2, 3, 4, and 2 that are not. Now before, I'd said that the most simple version of this is the pure circle cube, because you have a certain association that these edges and corners always have. These edges always have an association with a specific orbit that they're in, and these inner circle corners always have an association with the outer edge. So you might think at first blush that, well, all of these are basically fixed, all of these are basically bandaged down, so wouldn't they have the same kind of ease without having any difficulties with changing the configuration? And the answer is, well, no, it does get complicated. In terms of this guy over here, we're introducing a concept with these guys of bandaging. Now, in a way, there are bandaging with this. Some of these non-fixed centers are freely movable, and these fixed centers, you can say, are bandaged, perhaps. I just like to call them fixed because it can get confusing otherwise. But here, the true bandaging means that we're blocking some turns. So this turn over here is fine. I can move a circle side up here, and I can still turn. But if I try to take one of these and move it up to a circle side, it won't turn. So because of that introduction of actual bandaging where I can't move a face, well, then I have to do different strategies because I become blocked. When I become blocked, it means that I can only do 180-degree turns in certain planes, which means I had to do somewhat of cuboid strategies. Now this one, because it has two fixed circles over here, the two-circle face, looks a lot like the Saturn cube. Because notice this is fixed, just like this is fixed, but on all of these, it's not fixed. And so too, this is not fixed either. So these are not stationary, these move with it. But I'll tell you that the solve strategy, although this looks in form a lot like the Saturn cube, the strategy is very different, and it's very different because I can take this, move it into the fixed center, and move it around. Here, if I move this into the fixed side, I can't. So I have that extra bit of bandaging. So too, in looking at the structure of this, which is called the Crazy 3x3 plus 4 circle face puzzle, kind of a long name. You have 4 sides that can turn that have fixed centers, and then you have 2 sides that don't have any circles at all. Well, this looks a lot like the Venus cube. In many ways, it resembles that a lot as well, because with this one, you have 2 faces. See if I can find it. You've got this one, the green face, which is fixed, red face, which is fixed, blue face, which is fixed. So all of these have fixed centers, whereas the top and the bottom are non-fixed. Well, so too with this, the top and the bottom here, this is non-fixed, I guess you could say, but it just doesn't have any circles. And although this has the structure that's a lot like the Venus puzzle, I guess it would be more like this, that's a lot like the Venus puzzle, the solve is very different because none of these sides ever get blocked. No matter where I go, none of them are bandaged. So because of that, because of the bandaging that happens with this, I become very limited and very restricted in the kind of motions that I can do. So what's the best way of resolving this? What's the best way of solving the Crazy 3x3 plus 4 circle face puzzle, which in many ways resembles a lot like the Venus cube? So how do we navigate through this one? Well, it's important to understand that at its heart, it's like a circle cube. It just has bandaging because you don't have circles on every face. What that means is that just like I retain my association of these inner edges, these inner edges don't move. They remain fixed where they are. This will always be within this orbit. It will never leave. However, if I take a look at this, I can't say the same thing. Although this is within this orbit over here, if I turn it here, it doesn't move. What I can do is if I put it on this edge over here, if I put it on this face, I can now make this move and take it out of its usual assignment, out of its usual place. Now as it happens, I end up bandaging it so I don't have as many degrees of freedom of motion as I would with a true Venus puzzle. As you can see, I can take that out of here too, but I'm not bandaged. Here, I am bandaged. So all this means is that although I have similar restrictions with these faces here, I could potentially bring them out of their proper place and have to deal with strategies on how to solve that. Now I also want to point out the fact that although this is solved very much like a cube, because I'm restricted, if I make this turn over here and I can't do another turn like this, it moves very much like a cuboid. So I can't make a 90-degree turn and then make another 90-degree turn just after that. I've got to do 180-degree turns. So this strategy is going to have to be exactly like a cuboid strategy. So what do we do in terms of solving this one? Now I did do a tutorial on this, so I'm going to leave this to the side. We're going to go through how to solve this Venus-esque looking Crazy 3x3 4 circle face puzzle. So this is what I enjoy about these crazy puzzles, in that it takes more strategy, but luckily there's not a whole lot of new algorithms. As a matter of fact, I don't even know if I would call what I'm about to show you algorithms. I'm going to go through those first. They're really more complicated versions of commutators. Commutators are a very basic set of movements where you do like R, U, R, I, U, I, something that does a move then immediately undoes the move. But the first algorithm that I'm going to show is going to take the center here and is going to do a 3 cycle of edges rather. takes this edge, puts it here, this comes over here, and this comes over here. And that's going to become important at some point. So what's going to happen with this, if I want to do on the right side, this to here, this to here, and this to here. This is an R movement. I'm just going to go R to U, RI to U. And I'm going to do that 5 times, so that was once. Now I'm going to do it again. R to U, R to U, that's 2. R to U, R to U, that's 3. U, R to U, that's 4. R to U, R to U, that's 5. And what that effectively did is really just took this, moved it to here. This came to here, as you can tell, because this outer edge is the one that belonged here, and this came over to here. So that's a nice clean 3 cycle that you can do should you ever need to do that. So let's look at it from another perspective. Okay, let's say I want to do just the opposite. Move this left one to here, this to here. It's exactly the same thing, only kind of its mirror image. So that's going to be LI to U, L to U. That's 1, and do that 5 times. LI to U, L to U, that's 2. 3, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5. So there that is here, and again, it's a clean 3 cycle of these edges. So that's going to have use to us later. Well, here's another version of that commutator to look at. Let's take that same commutator, and instead of doing it 5 times, let's do it 3 times and see where the sparks fly. What this is going to do is this is going to start to cycle around my edges. So let's kind of pay attention and see what happens with that. So I'm going to do that 3 times starting on the right side. So R to U, RI to U, that's 1. R to U, RI to U, that's 2. R to U, RI to U, that's 3. So we're going to stop here and see what happened. You can see that all of my edges are the same. So if I stop at 3, the edges have recycled back, but let's take a look at the corners. The corner that was over here, which is the blue, red, and yellow, ended up where? Well, ended up over here. So this went over to here. And the one that was over here, which is the blue, white, and orange, went over here. So this went to here, this went to here, and this yellow, orange, and blue went over to here, and this green one went over to here. Well, that's pretty complicated. That was a 5 cycle. This went to here, this went to here, this went to here, and this went to here. I have a way where I can move the corners without affecting the edges. But doing a 5 cycle, that's kind of rough stuff. Reason being is it's kind of hard to predict where things are supposed to go when it's a 5 cycle, but at least we know that it can be done. Plus notice there's some rotation. This, when it came over here, we still had the blue on top. This, when it came here, flipped. This, when it came down here, just slid. This flipped over here, and this came over to here, and it flipped as well. So there's a lot of complexity to that. But I did want to point out that that's a way of cycling around corners without affecting edges, and that's going to have a utility with us at some point in the future also. So let's get it back. Okay. Now I want to show you one more algorithm to use, and actually if you understood what I just did and understand the algorithm that I'm going to show you now, then you could probably stop the video, scramble it, and see how you do, see how you fare, because I'm going to arm you with exactly the information, except for one key information that I'm not going to tell you right now until the opportunity arises. This is something that's going to actually cycle the corners. Now remember, in the solve of a pure circle cube, I ignored the corners. I ignored the inner corners rather, because by putting the edges in, as these edges were married to these inner corners here, I didn't have to worry about that. Put the edges in, the corners just get solved. With this, the corners can be pulled out of alignment, because this is normally married to this edge, right? But if I move it up here, and then move it like this, I've now pulled this away from this edge. So I could end up with a situation where I have the 3x3 solved, but these corners won't be where it needs to be. Well, what this algorithm is going to do, and the good news is it's not too different from just variations of what I just showed you, that commutator that I showed you, is on the left side here, it's going to take this to here, this to here, and this to here. So we're going to take our bottom left, move it up to the top right, move this to the back right, and move the back right down to the bottom left. So let's look at the commutator that does it. Now I'll tell you, it's not a clean algorithm. When that happens, they will be cycled, but I'm going to kind of take out some of the corners a little bit too, but that's easily placed back in. So let's see what happens when we do this. By the end of this, I'll have permuted these around. What you're going to do is start off with the same commutator on the right side, but once again just do it 3 times. The 3 times again is not going to affect the corners, the edges rather, but will affect the corners. So starting off on the right side, R to U, RI to U, that's 1, R to U, RI to U, that's 2, R to U, RI to U, that's 3. Now immediately do the same thing but on the left side. LI to U, L to U, that's 1, Li to U, L to U, that's 2, Li to U, L to U, that's 3. What you're then going to do as the bridge is you're going to go back to the R and just do a 2R. And now do the same thing exactly again. After doing the 2R, do the same thing, starting on the right side, R to U, Ri to U, that's 1, 2, 2, 2, 2, 3, 3, 3, 3. Go right to the left side, do the same thing. Li to U, L to U, that's 1, 2, 2, 2, 2, 3, 3, 3, 3. And then you're going to finish it off with another 2R. Bang, 2R. Now what you've done is you've actually taken out the alignment of the center corners from the outer corners, from the inner corners from the outer corners. What you're going to have to do now is just get the top back and get the bottom back. We're going to do corner swapping algorithm the same way that you do with the cuboid. So I see the green here. This is green, red, and white. I'm going to position this at the proper place to come over to here for the green, red, and white. And I'm going to swap this down here, going 2R, U, 2R, UI, 2R. It's a typical cuboid strategy. Then I'm going to place this one in. Now understand when I do that, I do placement parity with this, do misplacement here, but I'm about to put that back in by just finding the proper place where this goes. Orange and yellow comes over to here with the orange and yellow, 2R, U, 2R, UI, 2R. Then move this back in. So at the end of the day, the end result is I've got this one actually went to here, this went to here, and this went to here. It's kind of hard to see because it looks like I just swapped these two, but that's not what happened. This red one actually came from over here. So this was a clean swap of this corner to here, this to here, and this to here. Now if I want to do the same thing on the other side, let's say I want to do the same thing on the left side over here, this can come to here, this can come to here, and this can come to here. To demonstrate this better, you can do any type of deconstructing and reconstructing of the puzzle. Deconstruct it before doing the algorithm, reconstruct it after. So if I move this over here, this is just demonstrate the 3 cycle of it. This red will come up to here, this white will come down to here to this orange, and this orange will come over to here. So on the left side, rather, if I want to start on the right side here to start cycling the right to the left, I'll start with the left, do the same thing, just kind of the opposite of what I did on the right side. So do this, do that commutator 3 times again. That's Li to U, L to U, that's 1, Li to U, L to U, that's 2, Li to U, L to U, that's 3. Immediately go to this side, do the same thing on the right side. R to U, Ri to U, 1, 2, 2, 2, 2, 3, 3, 3, 3. Then what I'm going to do this time is do a 2L. 1, 2, and jump right into the second time doing the same thing. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Jump to the right side. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. And then just do a 2L over here again. Bang, bang. Once I've done that, I can reconstruct it by moving this back. And now I just go ahead and put this back in. It's just going to be 2 corners that I'm going to have to do. So this is the white and red. Match it up, find the white and red. Yellow and red. This comes down to here. 2RU, 2RUI, 2R. Find the other one. 2RU, 2RUI, 2R. And lo and behold, if I move this back to where it originally was, this red came over to here, this white came over to here, and this orange came over to here. So you can see that no matter how jumbled up I am, I can get these back in. So that's just a basic bit of information on solving this and the algorithms that are needed, but there's one key thing that I'm leaving out now, which is the notion of parity.